In this section, we will derive the algorithm for the least squares filter, recursive least squares filter. And what we have seen so far is that the error is given by the subtraction between the desired signal and the filter output. And filter output in turn is nothing but a dot product between the weight or the coefficient of the filter and the input to the filter. So we take this and we substitute here. So what we get in error is dn minus wn xn, that is equation 3. And then we define the cost function, which is sum of squares of errors. So this portion is the square of errors, and this is the forgetting factor, which we described in the previous section. So moving on, we have now one objective, that is to find a w which minimizes this square of errors. So how that can be done is by taking a derivative of this cost function with respect to the weight, because weight is the variable part in this whole equation, and we are supposed to tweak around with that weight so that this whole expression reaches to its minimum point, and after taking the derivative we equate it to 0. So this is how we're going to do it. So what is the derivative of, so in this entire expression, as you see, there is only one component which is having w, which is here. So that makes our life easy. So taking derivative with respect to w works out to, this is just a scalar without any component of w. So we take this whole expression first, and this is what we get. And then by chain rule, now we go inside this function and then do the differentiation. So dk doesn't have any component of dw, it goes to 0. And what remains is minus xk. And this whole expression will be equated to 0. So once we do that, what we get is we can take this 2 and minus sign on the other side and get rid of it. So what remains now is this xk multiplied by dk. So dk xk and minus k is equal to 1 to n again. And what we get here is wn x square. Now this is equated to 0. So what I'm going to do is I will take this expression on the other side of the equation. So what it becomes is this becomes this equation, and my objective is to find out the weight which minimizes this entire sum of squares. So I can rewrite this whole expression as dk xk lambda n minus k and x square. So this is a very important, n minus lambda raised to power n minus k. So this is a very important function. This upper part is nothing but it's a cross correlation between the desired signal and the input to the filter, and the bottom is nothing, the denominator is an autocorrelation of the input to the filter, which is x. So we'll go and find out this entire expression in a recursive form, and for convenience, just for a minute, I'm just dropping this term because it does not carry any component of w, and I will reintroduce this lambda later. I'm doing this just to simplify this entire development of this algorithm. It's just a scalar part which can be introduced later. What we can do is that we have to now, if you remember from our discussion on the recursion, we have to get the next weight in form of a recursive formula, which should look something like this. Let's go back to part 1 of this tutorial where we expressed the recursive form, and it was in this particular format. So can we put this weight calculation formula in a recursive form? Let's see. So what will be the next weight? N plus 1. It'll be nothing but k from k to n plus 1 term, and in the denominator we have dk xk, and in the denominator we will have again from k to n plus 1 xk square. Remember, I have dropped this term as of now, but we will come back to from both numerator and denominator, but I'll come back to it. I've done this thing only for simplicity. So we can try to redefine this, because now if you see this format, in this we have to express the new weight in terms of the old weight. So I have to do some manipulation to this formula so that it comes in this format. So the best way of doing it is, let me take the first n terms, that means k varying from 1 to n, and then the only term that is missing is n plus 1 term. So what is n plus 1 term? N plus 1 term is nothing but dn plus 1 x n plus 1. So this is equivalent to the numerator part, and the denominator can also be written in a similar fashion. So k going from 1 to n plus 1 xk square, and then, so not n plus 1 here, this is n, and we add the nth term. So in this n plus 1 term, so what is the n plus 1 term? X n plus 1 square. So this is a very convenient form in which I have expressed the next weight. And what I'm going to do now is I'm going to split the numerator in two parts. One is this, and the other is this part. So let me do that. So I have k going from 1 to n, tk, xk, and under this I have again k going from 1 to n, xk square plus x n plus 1 square, and then I have another part, which is this part. So this is nothing but d n plus 1 x n plus 1 divided by the same denominator, which is x n xk square plus x square n plus 1. So from now on, these are two different expressions. I will take this and this separately and try to manipulate this whole expression in a manner that it comes into a recursive form. So I'll call this as expression 1, and let this be expression 2. So let me start with the expression 1. So remember, I have to convert this into a recursive form. So let's do some manipulations to this. What I can do is, so firstly let me write down this whole expression. This is k is equal to 1 dk xk, and now to this expression I can multiply this part, which is nothing but, if you remember, I can write k going from 1 to n xk square, and I have similar thing in the numerator. This is just a manipulation to arrive at something. So if you now see this portion, this is nothing but wn. So since we have dropped these two terms, so wn is this particular expression, and this is exactly that is matching with, I'm talking about this, and this is exactly the same thing which we have done here. So what it becomes then is wn multiplied by sigma from k to n x k square, and denominator remains the same, which is this one. So there's a manipulation. Now if you see in this whole expression, we have brought the old weight into picture. So we are moving towards the recursive formula, and that's why this manipulation was done. Now, can we do something more? Can we manipulate this expression further so that we simplify this expression further? So I think we can take advantage of this denominator. So this denominator has xk square term, and also x square n plus 1, but the numerator part is missing that. So what I'll do is I will do some manipulation here again. I can write this expression once again as, and here is the manipulation. So I am adding x square n plus 1, and I'm also subtracting it. I'm permitted to do that. divided by the same denominator. Now once again, I'll again split this into two parts. The first part is this, and the second part is this. And essentially what will happen is, you can see clearly that for this part, both the expressions in numerator and denominator are the same, and they will cancel out. So this is how it will look. And here also the denominator is going to be the same. And as you can see, these are two just the same. So pretty neat so far. So this first term becomes 1, and I'll do one more manipulation here. I will write this x square as x n plus 1 multiplied by x n plus 1, and then divided by the same denominator. Remember, we are just dealing with expression 1 so far. And here again, I'm going to do some manipulation. I'm going to declare this part as an alternate term called k n plus 1. So let me just write it down. Let k n plus 1 be x n plus 1 divided by k is equal to 1 going up to n. So this is an important expression, and later on you'll see that this actually becomes the gain term. So the whole expression then reduces to 1 minus k n plus 1 x n plus 1. So for the time being, this is a very good result. We will stop here. We will not do any further simplification.